Okay, let's get started. Good afternoon, everyone. Let's start with one of our policies, as always. This one today is about, we started. Can you sit down, please? Thank you. All right. So the policy that we are going to go over today is course materials copyright, which basically says that if you are using these materials from this course, you can't use them to get any money. Basically, that's the gist of this policy. So yeah, the content is made available only for your personal, non-commercial, educational, and scholarly use. And if you want to read more about that, you can go to Code of Student Rights and Responsibility, and then there is a section regarding use and distribution of class content. All right, that's all about policies. I did send an announcement today about, I'm looking basically for a team of 2 that is willing to take another person onto their projects. So if you are such a team, please contact me or the TAs immediately after the class, and we will add another student to your group. We would highly appreciate that, such that we don't have to have a group of 1. So if you are in a position to do that, please be generous and do it. Okay. Besides that, there aren't any special announcements. We did release the 3rd homework today that's due in 2 weeks. So just have that in mind, that if you haven't started to work on the 2nd one, which is due in 1 week, it's probably a good idea to start now, such that you don't have too many at the same time. Okay, so let's move on to our lecture, which is basically finishing up minhashing. We didn't tell everything we wanted to go tell last time. And then we are going to go into the details of something that's called locality sensitive hashing, or LSH. So going back to the previous lecture, we kind of finished up on a note of saying that we can estimate Jacquard similarity by calculating those signatures and then comparing 2 signatures of 2 different data sets, excuse me, 2 different sets by checking how many times they match in their dimensions. That's what this formula is saying. And here we have one factor, which is this number k here. That's the number of min hash of the hash functions we are going to use. And there was a question of how many hash functions we should use to get a good estimate of a Jacquard similarity. And that's not something we had covered last time, so let's get into that. So the question is, sorry, my thing is falling down. How large should k be? Where k is the number of hash functions we are using to construct our signature. K is also the dimension of the signature, because we are going to put the outcome of the hash function into the signature of each one of them. All right. How large should k be? And to answer this question, we are going to use a more general framework, not a framework that's not only applicable to this question in this specific situation, but a framework we are going to use to think about how to aggregate more and more data to get better estimates in general in data mining. And this framework is called probably, approximately, correct, or short for it is back, which makes for a great band name. All right. So to talk about probably about PAC, we need to introduce some variables. First, we are going to have our X hat, which is an estimate. This is a random variable. And if you remember from the lecture last time, we had defined one such variable. Let me try to find it. So here we have defined one such random variable where we had this k random variables XL, and then we took their sample mean, and then this is what gave us the estimate of Jacquard similarity. All right, we are going to introduce, oh no, this is ugly. We are going to also introduce the expected value of this random variable. So in our example, that would be Jacquard similarity. And we are going to need two scalars. One is delta, which is going to be in the range from 0 to 1. And that's going to be our probability of failure. So this is how much failure we accept. So if we have delta equal to 0.1, we accept 10% of failure. So in 10% of situations, we won't get a good estimate of, let's say, Jacquard similarity. And then we have epsilon, which is some number greater than 0, which is our error tolerance. And this serves to say, well, how good an estimate is, and you will realize how it is used in a second. So when we talk about PAC, we are basically talking about bounds that have this formulation, that the probability of a difference between random variable x hat and its expected mean is larger than epsilon should be smaller than delta. So being larger than epsilon is unwanted. We don't want it to be larger than epsilon. That means that this is not a good estimate, and we want that to happen less than delta times. If delta was 0.1, less than 10% of the time. Equivalent way of writing this is to say this is a probability of the difference between the x hat and its expected mean is smaller than epsilon, which is desired, is larger than 1 minus delta. So our random variable will be a good estimate of, let's say, Jacquard variable. If their difference is smaller than some number epsilon, a small number, should be larger than, let's say, 0.9. So in 90% of situations, we should have a good estimate of Jacquard similarity. Okay, so now, usually we, when we talk about PAC, at least in this course, we will talk about something called Chernoff-Hoeffding inequality. And how we get to that, we won't derive it completely, but I will just mention one basic ingredient that you need, and that's central limit theorem. And you all, I'm sure, know what this is. Because this is the most classic theorem you have covered in any probability course you have ever taken. Let me just go like this, like this. Okay. Which basically says if you had, let's say, n random variables and they are distributed, you don't even know how they are distributed, you just know they have some mean and variance. If you take a lot of them, if we push it to infinity, then their sample mean, when we take their average, we will get a random variable that's normally distributed. That's what central limit theorem is saying. So when we write it in a more mathy way, we have, n random variables, and each one of them is sampled from some distribution. F is fixed, potentially unknown, has a mean of mu and variance sigma square. And then when we take the sample mean of these n random variables, which means that we just take their average, and if we take many, many of them, we know that then this random variable will behave like normally distributed variable. And this will go to 0 because if n goes into infinity, 1 over n goes to 0. All right, so that's the classic theorem we know. And then if we would apply this, combine this theorem with PAC, we would get something called Chernoff-Hoeffding inequality or bound. Just a heads up that if you look at the class calendar and click on those notes, this part about PAC and this bound is actually in the notes for the second lecture. So basically what I'm writing here, you can also find there, just in case you like to look at those notes. Okay, and if we would combine CLP with PAC, which we will not derive here, you would get the following formulation that if we have our random variables, which are independently and equally distributed. And also they are such that they are bounded by this capital delta here for every one of them. Okay, we don't have to write that. Then if we take a random variable, A, which is their sample mean, we would get this bound that the probability of A being different than its expected value is larger than some lambda number that's larger than 0 is smaller or equal to 2 times e to the power of r lambda square over 2 times delta square. So that's the bound. And that's not the only formulation of this bound. Another useful formulation of it. Sorry? Oh, okay. This is lambda. I'm remembering the reflector so well. Yeah. You can call it anything, basically. Yeah, the notes have used this for these letters, so I stick with that. Yep.
Like this quantities are here in the negative parentheses RL.
Yeah.
Oh, is that e to the?
Yeah. Okay, I don't know how to make it.
No,
yeah, that's basically, if you remember the mean of normally distributed random variable, that's the connection, basically. That's how it occurs, and that's what we get from the central limit theorem. Okay, I am moving on. Is that okay? Yeah, go ahead. Yeah. It can be different for each random variable. In a specific example, we'll see in a second, they will all have the same bounds. Yeah. Okay. All right, moving on to the different formulation. Oops. So this is just another form of the CH bound, which will be useful for us in a second. So again, we have our random variables, and again, they are limited by some numbers, here A and B, and we will define delta I as the difference between BI and AI. We are going to define M as the sample mean. Not the sample mean because we don't have 1 over M here, so we don't have it. So it's a slightly different notation. And we have alpha equals, sorry, not alpha, lambda greater than 0, then the probability that m and its expected value are larger than lambda is again smaller than 2 times e, but we will have slightly different version here. We'll have minus 2 times lambda square, and then we are going to sum these r delta i's. Okay. Now just check that I didn't make a mistake in my notes about whether we do have denominator here or not. Okay, yeah, this is correct. So we don't have the denominator for the random variable m like we had before.
Is this the form that's written in the notes?
Yeah, it is. So if you go at notes for the second lecture, statistical principles, at the end of it, you will have both of these bounds written there. Yeah. Okay, so this bound is going to be useful for answering the question we have, which is how many hash functions how many hash functions do we need to get a good estimate of Jacquard similarity? Yeah.
So if you go to the previous slide, delta I, that's just a constant where these divide the maximum makes by.
Yeah, it's
so the sum would just be the R times delta.
No, because they can be different for every I. We have different AI and BI for every random variable xi.
So the x sub I don't need to come to the same distribution.
They can come from different distribution and still have different values, like counting something, right?
Okay.
Yeah. Okay, moving on to what we want is that Jacquard similarity between two sets, Si, Sj, and their estimated Jacquard similarity is smaller than some small number epsilon. Okay, let's remind ourselves of how did we define xi's in the previous lecture. So we had the indicator function, remember, which is a function which takes 1 if something is satisfied, otherwise 0 if it's not. So we get value 1 if the mean hash values of Si are equal. Okay, and we know now that this is going to be bounded by 0 and 1, right? Because this random variable either takes the value of 0 or 1. We are going to define m as their sum. Okay, we have k of them. And we know that expectation of this random variable equals to sum of the expectations of these individual variables. And last time we have talked about how much this is. Basically, expectation definition is the value times the probability. Probability equals the Jacquard similarity. And we only count those where we have 1, zeros cancel out. So this basically equals to Jacquard similarity of Si, Sj. And when we sum k of them, we will get k times the Jacquard similarity of Si, Sj. All right, so now we are going to go and use some of our bounds. We are going to measure the probability of our estimated Jacquard similarity. And the difference with the real Jacquard similarity. And we are going to set this to be larger than alpha over k. And don't think too much about why this is alpha over k now, because the point is that we are going to use some other numbers to kind of get to what we want. So you can think about, if you are looking back at those random bounds, they said these can be any numbers. So just bear with the derivation for a moment. We put this. We can then, this is equal to writing, you just put k inside the absolute value, so we can have k times Jacquard, estimated Jacquard similarity, minus k times Jacquard similarity. So this is basic arithmetics. And this is going to be larger than lambda. Okay, and now you probably notice that, okay, here we have the same thing we have here.